This is one of my favorite topics in calculus, implicit differentiation. And this is a very powerful, very elegant way of taking derivatives, which we've really kind of done already, and I'll make that connection in a few minutes here. But when we've been doing derivatives so far, they've all been functions. We've already had y isolated in all of them. But implicit differentiation allows us to take derivatives of equations no matter how they're written, and they don't even have to be functions. So for example here, y squared equals x is a parabola set vertex at the origins, opening to the right, and definitely not a function. And for this, I am going to be using Leibniz notation just because it makes it much easier for us to look at a very specific piece of information, namely what our derivatives are with respect to. So we need to know what variable the derivative is with respect to. And the reason for that is anything that's not this variable, we have to treat like a function. So any other variable is a function, and we need the chain rule on it. So, for example here, y squared equals x, I'm going to leave it just like that. So, and I'm going to do the derivative of the right-hand side first. So the derivative of x is 1. And we're looking for our derivative with respect to x, so I don't need to worry about chain rule here. Then y squared, its derivative is 2y, but this is not an x, and so we have to pretend that y is a function of x. And so this is a function inside of being squared. So the 2y is the derivative of the squaring, but then I need the derivative of y with respect to x. Well, I don't know what it is, so I just write dy dx. And this is what I mean by us doing the chain rule. So derivative of y squared times the derivative of y. I could even think about it with x, so derivative of x is 1, but then times the derivative of x with respect to x, do the chain rule, well, the dx's cancel, and that's gone. So then it says we want to actually know what is dy dx, so my dy dx is here, I just need to isolate it, and so dy dx equals 1 over 2y. It is not unusual, especially in things that are not functions, to see a y value in the derivative. We haven't seen it yet because we've only dealt with functions, and it's rare to see a y value in a function's derivative. But non-functions, it's pretty common to see y in the derivative. But even with what we've done before, where we've dealt with functions, we can think of it as implicit differentiation as well. So here, for y equals x to the fifth, if I wanted to find dy dx, again, it'd be with respect to x. So the derivative of x to the fifth is 5x to the fourth. Because I'm going with respect to x, I don't need to worry about chain rule for that. Derivative of y would be 1, but then that is not an x, so I would need the chain rule on it. And I would still get that dy dx is 5x to the fourth. The next video is going to go through some examples of doing this.